Look at something red in your field of vision right now. It can be anything: an apple, a shirt, any object. You see red, obvious, natural, unquestionable. That object is not red. In fact, nothing is. This isn't a philosophical question or a play on words. It's a precise physical statement, and it was exactly this kind of statement that Richard Feynman spent his entire life making. Feynman won the Nobel Prize in Physics in 1965. He developed the most precisely tested mathematical framework in the history of science, and whenever someone offered a surface-level explanation for anything, he couldn't swallow it. He would say, "You've given me a name for the process, not an explanation." Learning the name of a thing is not the same as understanding the thing. There is a standard explanation for color. You know it. It appears in textbooks from high school to university. It's repeated by teachers and science communicators, and it seems complete. It's elegant, consistent, backed by centuries of science. Feynman would say exactly this about it. "You've given me a map, a beautiful map, well drawn, but one that describes the wrong territory." For over 200 years, this explanation convinced physicists, teachers, and curious minds that the matter was settled. And in a superficial sense, it was. The map works for navigating everyday life. But Feynman wasn't interested in maps that work. He was interested in maps that describe the real territory. What this explanation gets right, what it leaves out, and where it stops being physics and becomes the illusion of physics, that's what this video will take apart. Layer by layer. Starting with what seems obvious, moving through what physicists know but rarely explain in public, all the way to where Feynman arrived when he pushed reasoning to its limit: quantum electrodynamics. And by the end, you'll understand color at a level most people will never reach, not because it's too difficult, but because no one has ever bothered to explain it properly. So, what did Feynman see that you haven't seen yet? Let's start from the beginning. The model you learned in school. White light contains all the wavelengths of the visible spectrum. When that light strikes an object, the object absorbs some wavelengths and reflects others. The reflected wavelengths enter your eye, stimulate the receptor cells in the retina, and the brain interprets that signal as color. This is correct. This is the official narrative, and it works. Newton proved in 1666 that a prism separates white light into a rainbow of colors. What had seemed to be the most fundamental property of light, its color, turned out to be a mixture. White light is not simple. It is the sum of an entire progression: violet around 380 nanometers, indigo, blue, green, yellow, orange, and red around 700 nanometers. Each color corresponds to a specific wavelength. Newton didn't invent the colors of the rainbow. He revealed that they were already there, layered on top of one another, inside the white light that had seemed uniform. The model that emerged from this discovery is elegant. A tomato reflects wavelengths around 700 nanometers and absorbs the rest. That's why it appears red. A leaf absorbs red and blue wavelengths reflecting green. Coal absorbs almost everything. Each object has a specific absorption and reflection profile, and that profile determines its color. The model solves everything. This is where the trap snaps shut. Why does the tomato absorb those specific wavelengths and not others? The model says that it absorbs. It doesn't say why. It says that different objects have different absorption properties, but it doesn't explain what determines those properties. The question, why does this object absorb this wavelength, goes completely unanswered. The model presents the result as though the result were the explanation. It's like explaining why a particular intersection is dangerous by saying that many accidents happen there. You've described the pattern. You haven't explained the mechanism. Feynman had a name for this kind of explanation. He called it knowing the name of the thing without knowing anything about it. The standard model of color names the steps: wavelength, absorption, reflection, cone, perception. Each step has a name. Each name has a definition. And the impression of understanding this creates is so convincing that most people, including most physicists, when they're not thinking carefully, believe the matter is closed. It isn't. The question, why, remains unanswered precisely at the point where things get interesting. The answer lies one layer deeper. at the level where matter is made of almost nothing. The real story begins with James Clerk Maxwell in 1865. Maxwell did something that transformed physics forever. He unified electricity, magnetism, and light into a single mathematical framework. Until then, they were three distinct phenomena, studied by different people, with different equations. Maxwell showed they are three faces of the same reality, the electromagnetic field. Light is an electromagnetic wave, an oscillation of electric and magnetic fields propagating through space at 300 million meters per second. This is not an analogy. It is what light literally is. And this means that visible light is just a tiny sliver of a much broader spectrum. Below violet, ultraviolet, X-rays, gamma rays. Above red, infrared, microwaves, radio waves. The entire range you call light, from 380 to 700 nanometers, occupies an extraordinarily narrow window within a spectrum that spans from fractions of a nanometer to hundreds of kilometers in wavelength. Why exactly this window? Because it was the window for which evolution built receptors. There is nothing physically special about this range. It is the useful range for creatures that live in sunlight on Earth's surface. A biological choice, not a physical boundary. An evolutionary solution to a survival problem, not the definition of what light is. The decisive moment came in 1905, when Einstein explained the photoelectric effect. Maxwell described light as a wave, and he was right. But Einstein showed that light also behaves as a particle. Each packet of light is a photon, and photons carry energy, a specific amount determined by wavelength. Ultraviolet photons carry more energy than blue light photons, which carry more than red light photons. This energy relationship is direct and literal, and it leads us to the real mechanism. A mechanism that is, at the very least, unsettling. The reason a tomato is red has far less to do with the tomato's surface than with what the electrons inside the tomato are allowed to do. Electrons in atoms and molecules cannot occupy just any energy level. They can only exist at specific quantized levels. It's like a staircase with separate steps and empty space between them. You can be on step 1, 2, or 3, but never in between. When a photon strikes a material, one of two things can happen. If the photon's energy exactly matches the difference between two allowed electronic levels, the electron absorbs the photon and jumps to the higher level. The photon disappears. If the energy doesn't match any allowed level, the photon is re-emitted, reflected. The electronic structure of a material, the specific arrangement of its energy levels, determined by chemical composition and molecular architecture, determines exactly which wavelengths are absorbed and which are reflected. The red of a tomato is the electronic signature of lycopene molecules. It is not a surface property, it is quantum physics. And if you think reflection is light bouncing off a surface and coming back, like a tennis ball against a wall, that picture is also wrong. The atom is composed almost entirely of empty space. The nucleus occupies an infinitesimal fraction of the total volume. Electrons are probability distributions, not solid spheres. There is no surface in the classical sense. What exists are fields and probabilities. But before we reach the deepest level, the theory that Feynman built to describe this interaction with absolute precision, there is another side of the story that the textbook model ignores entirely. What happens after light reaches your eye? Here is a question that seems simple, but will change everything. If you turn off all the lights in the room, where is the color of the apple? The naive model would say, the color is stored in the object, waiting to be revealed by light. But you have just seen that color is the result of an interaction between photons and electrons. It doesn't exist without both sides of the equation. In darkness, there are no photons. There is no interaction. So where is the color? Even more unsettling, color isn't even in the light that reaches your eye. It's in your head. The human eye has three types of receptor cells for color, called cones, S, M, and L. Sensitive to short wavelengths around 420 nanometers, medium wavelengths around 530 nanometers, and long wavelengths around 560 nanometers. These three types of cones have sensitivities that overlap extensively. They do not each detect a color. They detect signal intensity across a range, and all three ranges cover a large portion of the visible spectrum simultaneously. What the brain receives is not color itself. It is three numbers, three response intensities from the three types of cones. And from those three numbers, the brain constructs the experience of color. Three numbers. That is what describes the entirety of your visual experience of color, not the full richness of the actual electromagnetic spectrum. Three channels of information, processed by neural circuits that evolved over hundreds of millions of years. And here comes the definitive proof that color is not a physical property of the world: metamerism. Take two completely different objects, one with a specific mixture of pigments, another with an entirely distinct spectral composition. Under a specific light source, both produce exactly the same response pattern in your three cones. Result, you see them as identical, the same color, indistinguishable, but change the light source. Now the two objects reflect different spectra, and suddenly they appear completely distinct. One might look orange, the other brown. The color that seemed identical was not in the objects. It was in the interaction between object, light, and brain. Feynman would have recognized this immediately. It is exactly the kind of result that shows that the object has this color is not an explanation. It is a convenient shorthand that works as long as conditions are fixed and fails the moment you question any variable. This is not a special case or an optical trick. It is the fundamental structure of the system. Color is a category that your brain imposes on the world, not a property that the world possesses independently, and this has direct consequences. With two types of cones functioning instead of three, dichromacy, the color space the brain can construct is different, not inferior. Different. It is another categorization system running on the same physical reality. And then there is the mantis shrimp. This crustacean has 16 types of photoreceptors. 16. Where you have 3 channels, it has 16. You might imagine it sees a far richer version of color than you do. But the reality is stranger. The mantis shrimp appears to use its extra photoreceptors not to expand fine spectral discrimination, but to categorize colors faster and more efficiently. A completely different processing architecture, built to solve completely different problems in its environment. There is no universal color experience. There is the human version, and dozens of other versions in other species, each one built to solve distinct problems about the physical structure of the world. Color is not in the world. It is in the contact between the world and the nervous system. But something in the world triggers that construction. And understanding what that something is, at the most precise level physics has ever reached, required Richard Feynman. Richard Feynman published QED, The Strange Theory of Light and Matter in 1985, a layperson's version of the theory he developed in the 1940s and 1950s, which earned him the Nobel Prize. And at the beginning of the book, he issued a warning. The theory is strange. It goes against every intuition you have. You will want to ask, but how is that possible? And the honest answer is that nobody knows how it is possible. We know what happens, and we know how to calculate what happens with staggering precision. But the picture the mathematics paints of the world does not correspond to any familiar object you have ever seen. QED, quantum electrodynamics, is the most precisely tested theory in the history of science. It predicts the magnetic moment of the electron with a precision of approximately 10 decimal places. The agreement between theory and experiment is so exact that it would be equivalent to measuring the distance between São Paulo and Tokyo with a margin of error the width of a human hair. And what does this theory say about reflection? Feynman said, if you truly want to understand how light interacts with matter, you have to completely abandon the classical picture. There is no surface. There is no bounce. There is no photon striking and being sent back like a ball. That picture is not a simplification. It is a mistake. What exists is probabilistic interaction between photons and electrons. When a photon approaches a material, there is no predetermined outcome. There is a probability amplitude for each possible result: absorption, reflection at various angles, transmission. Feynman developed a technique called the path integral, or sum over histories, which calculates these outcomes in a way radically different from everything that came before. The central idea is this: A photon does not take a single path from A to B. It takes every possible path simultaneously. Each path has an amplitude, a number that carries phase information. The observable result is the sum of all these amplitudes. For most trajectories, the amplitudes cancel each other out, the phases oppose. Only certain specific trajectories, where the phases align and reinforce each other, contribute meaningfully to the final result. What we call reflection, light returned from a surface, is the emergent pattern of billions of summed amplitudes. It is not bouncing, it is mathematics. The direction in which light reflects is not the result of a simple mechanical law. It is the path along which amplitudes add constructively. Think about what this means. The light you see reflecting off this object, the light that creates the experience of color in your mind, did not come from a direct bounce. It came from the interference pattern of probabilistic amplitudes calculated across every possible trajectory the photons could have taken. The world you see is the emergent pattern of a quantum calculation happening every fraction of a second, on every surface, at every moment. And the selection of wavelengths, why some are absorbed and others reflected, now has a mathematically complete description. The photon's energy must match a permitted electron energy level for the absorption amplitude to dominate. But QED goes further. It calculates the exact probability amplitude of every possible trajectory, the paths that build up and the ones that cancel out, the precise way each specific material selects which photons stay and which escape. The color of a material is the quantum signature of its electronic structure, and QED calculates that signature with a precision no previous theory could achieve. Let me show you what this means in practice. Copper has that specific copper color. The energy band structure of copper's electrons, determined by the element's atomic structure, permits transitions that preferentially absorb blue and green light, reflecting red and orange. It is not paint. It is the quantum fingerprint of copper's electrons. And gold. Gold should look silver. If you look at silver, an element close to gold on the periodic table, with a superficially similar electronic structure, you see a white silver metal that reflects equally across the entire visible spectrum. So, why is gold golden? The answer involves special relativity. The inner electrons of gold, being close to a nucleus with 79 protons, are pulled with such force that they move at approximately 58% the speed of light. At that speed, relativistic effects are significant. The relativistic mass of the electron increases. The inner orbits contract. This modifies the energy levels of the outer electrons, specifically, shifting the absorption band toward shorter wavelengths. The result? Gold absorbs blue light and reflects yellow. The color of gold is a relativistic effect. Without Einstein's special relativity, gold would appear silver. This is what it means to understand the real mechanism. Not just describing that gold is golden, but calculating, from the principles of quantum electrodynamics and special relativity, exactly why. Now that we have the real model, we can go to places where the naive model simply fails. Why is the sky blue? You've probably heard the answer, Rayleigh scattering. But what does that actually mean? Sunlight passes through the atmosphere, where it encounters nitrogen and oxygen molecules. These molecules are much smaller than the wavelengths of visible light. When a photon interacts with a molecule of that size, it can be scattered, emitted in a completely different direction. This happens because the molecule is shaken by the photon's electromagnetic field and re-emits radiation, and the efficiency of that re-emission is not uniform. It varies with the inverse of the fourth power of the wavelength. This means that light with shorter wavelengths is scattered far more intensely than light with longer wavelengths. Violet, at the short end of the visible spectrum, is scattered about 10 times more than red. Blue comes right behind it. When you look at any part of the sky that isn't the sun directly, you're seeing light that has been scattered toward you, and that light is dominated by the short wavelengths. Why is the sunset red and orange? At dusk, sunlight travels a much longer path through the atmosphere to reach you, because the sun is on the horizon, not at the zenith. Along that extended path, almost all the blue and violet has already been scattered in other directions. What remains and keeps traveling to your eye is dominated by the longer wavelengths, red and orange. The blue of the sky and the red of the sunset are the same phenomenon seen from different angles. Rayleigh scattering is a direct consequence of the quantum interaction between photons and molecules. The textbook model couldn't predict this precisely. The correct model predicts it exactly. But let me show you something that will seem impossible. A color that exists in no pigment, in no atom, in no molecule, yet one you see with absolute clarity. The morpho butterfly. This South American species has wings of an absolutely vibrant metallic blue. But those wings contain no blue pigment. Zero. If you ground the wings into powder and mixed it with water, the mixture would be translucent or brownish. The blue disappears, because the blue never existed in the pigment. It exists in the nanoscale structure of the wings. The scales of the morpho's wings have a repeating architecture of ridges and grooves, spaced on the order of hundreds of nanometers. When blue light strikes this structure, reflections from different layers interfere constructively. The amplitudes add up, exactly like the photon paths Feynman described. For other wavelengths, the interference is destructive. The amplitudes cancel out. The result is selective reflection of blue, pure structural color. And the color shifts with the viewing angle. Tilt the morpho's wing, and the color shifts toward green or darker blue, depending on how the interference geometry changes. The physical structure is the color. There is no separation between the two. The same physics appears in peacock feathers, in opal gemstones. No pigment, pure interference at the nanoscale. Why do metals look metallic? Metals have free electrons that aren't bound to specific atoms, but move through the material's crystal structure. These free electrons can absorb and re-emit photons across a wide range of wavelengths, nearly the entire visible spectrum. Broad reflectance across all wavelengths equals the metallic sheen you recognize. The difference in appearance between gold, silver, and copper is exactly which wavelengths those free electrons interact with most strongly. And you already know that for gold, part of that difference comes from relativity. What if I told you that you're blind to most of what's happening around you right now? Bees see in ultraviolet. Many flowers that look simple and uniform to you have complex UV patterns that guide bees directly to the nectar. Patterns completely invisible to the human eye. The flower that looks yellow to you is an elaborate landing map for the bee. Pit vipers detect infrared with specialized organs in the snout region, a way of seeing the heat emitted by warm-blooded prey in total darkness. The window of 380 to 700 nanometers that you call visible light is an evolutionary solution, not a cosmological privilege. The world is full of information at wavelengths you will never perceive directly, and that world is just as real as the one you see. The word color, curiously, didn't stay confined to the visual phenomenon. Physics borrowed it to name something entirely different. In particle physics, there is a theory called quantum chromodynamics, QCD. It is the theory of the strong nuclear force, the force that binds quarks together inside protons and neutrons. Without it, atomic nuclei would not exist, and therefore, no atoms, no molecules, no matter. Quarks, the fundamental particles that make up protons and neutrons, have a property that physicists needed to name. This property exists in 3 distinct values and follows specific combination rules. 3 quarks with different values combine into a neutral state, just like 3 light sources, red, green, blue, combine into white. Physicists needed a name for a property with 3 values that combine into neutrality. They chose color charge, red, green, blue, as color charge. The neutral state, colorless. QCD was formalized in the 1970s, and the name stuck. It has absolutely nothing to do with visible light. Quarks don't emit visible light. Red as a color charge is not the red you see. It's a label, a mathematical convention to distinguish the 3 states of a quantum field that has no visual analog of any kind. But the structure coincides in a way that's worth pausing to consider. The human visual system is 3-dimensional. 3 types of cones, 3 parameters that determine your entire experience of color. Color charge is 3-dimensional, 3 values. In both cases, 3 states that combine into neutrality describes the fundamental structure of the system. It's not a deep physical coincidence, it's a structural one. Physicists looked for an analogy in the everyday world for an abstract system with three values. The most natural analogy for three elements that combine into neutrality was the primary colors of light. It worked as a mathematical metaphor, and the name stuck forever. The word color was borrowed twice by physics. Neither use corresponds exactly to what you think of when you think of color. And that says something about the concept itself. The three-dimensional structure the brain uses to map the visual world is sophisticated enough to describe the interior of protons. The language of perception, physicists discovered, runs deeper than anyone expected. What does this mean for the red you saw at the beginning of this video? That red object you looked at in the opening, what is it now? You know the object has no color. It has a specific molecular structure, arrangements of electrons in certain atoms with certain quantized energy levels. When photons from the sun strike that material, the photons whose energies match, allowed electronic transitions are absorbed. The photons whose energies don't match are probabilistically re-emitted in all directions, with amplitudes calculated by Feynman's quantum electrodynamics. Some of those photons reach your retina. They stimulate the L cones more than the M cones, and far more than the S cones. The nervous system receives three numbers. The brain processes that signal and produces an experience, a quality that you call red. The red wasn't in the object, it wasn't in the photon. It was in the relationship between the quantum structure of the material, the physics of light propagation, the architecture of your photoreceptors, and the neural processing of your visual cortex. That's what Feynman was pointing at. Not just about color, about any explanation. He insisted, there is a difference between describing what happens and understanding why it happens. The textbook explanation of color describes the steps. QED, together with neuroscience and evolutionary biology, reveals the mechanism. And the mechanism is what you just saw. The world is not colorful. The world has structure, electric fields, quantum states, geometry at the atomic scale. Color is the perceptual interface that the human nervous system built over that structure across hundreds of millions of years of evolution. It is a remarkably sophisticated biological technology for extracting information about the environment from differences in the electronic structure of materials. That doesn't make color less real. It makes color more interesting, because it reveals that the most immediate and everyday experience you have of the world is, at its foundation, the result of quantum and neural engineering operating in concert. Seeing through Feynman's eyes doesn't mean seeing less color. It means understanding what color actually is. Not a property the world possesses, but a question your nervous system asks of the world. From this single principle, that reality has structure, not color, and that color is what emerges when that structure meets a nervous system. Everything follows. If this kind of explanation resonates with you, if you enjoy getting to the real mechanism behind things that seem obvious, this channel has much more of this type of content. Subscribe so you don't miss the next videos. And if you think someone you know should see this side of color that no one has ever properly explained, share it.